According to National Electrical Code Section 250.66, the grounding electrode conductor, or GEC, for a building or structure served by a single service shall be sized based on the largest service entrance conductor. In this case, there is a 5-gang meter center with multiple service entrances. Two options exist: firstly, a single GEC to one water line, and secondly, separate GEC to each water line. The first option involves running a single grounding electrode conductor from each service to one designated water line. The grounding electrode conductor is sized according to National Electrical Code Section 250.66 for the largest service entrance conductor. Then, all of the water lines in each unit subpanel are bonded to this designated water line using a bonding jumper. The second option is to run a separate grounding electrode conductor from each service to each water line in each unit. Size each grounding electrode conductor according to National Electrical Code Section 250.66 for the respective service entrance conductor. Do not bond the water lines in the subpanels in this case. Both options are acceptable according to the National Electrical Code. However, the first option, a single grounding electrode conductor to one water line, is typically preferred for several reasons: 1. Simplicity, 2. Reliability, and 3. Code compliance. Regarding simplicity, it requires fewer materials and labor to install. Regarding reliability, a single grounding electrode conductor provides a more robust grounding path than multiple grounding electrode conductors. Regarding code compliance, it meets the requirements of National Electrical Code Section 250.66, which allows for single grounding electrode conductor to be used for multiple service entrances. In conclusion, the preferred method for grounding these condos is to run a single grounding electrode conductor from each service to one designated water line sized according to National Electrical Code Section 250.66 and bond all of the water lines in each unit subpanel to this designated water line. It's important to understand the requirements outlined in NEC 250.66 when dealing with grounding electrode conductors. The size of the grounding electrode conductor is directly related to the size of the service entrance conductor. This ensures that the grounding system can effectively handle fault currents. When multiple services are present, as in a multi-unit dwelling, the code allows for some flexibility in how the grounding electrode conductors are configured. Using a single, appropriately sized grounding electrode conductor connected to a common grounding electrode, such as a water pipe, can simplify the installation and potentially improve the overall effectiveness of the grounding system. The alternative approach of running individual grounding electrode conductors to each service entrance is also permitted, provided that each conductor is sized according to the corresponding service entrance conductor. However, this can lead to a more complex and potentially less reliable grounding system. Bonding the water lines in each unit subpanel back to the main grounding electrode is an important aspect of ensuring electrical safety. This bonding creates a low impedance path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The size of the bonding jumpers used for this purpose must also be in accordance with the NEC requirements. When deciding between the two grounding options, several factors should be considered, including the cost of materials, the labor involved, and the potential for future maintenance. In many cases, the single grounding electrode conductor approach will be more cost-effective and easier to maintain. However, the specific circumstances of each installation should be carefully evaluated to determine the best approach. It's also important to consult with a qualified electrical inspector or engineer to ensure that the grounding system meets all applicable code requirements and is properly installed. A properly designed and installed grounding system is essential for protecting people and property from electrical hazards. By following the guidelines in NEC 250.66 and considering the specific needs of each installation, it is possible to create a safe and reliable grounding system for multi-unit dwellings. The NEC provides specific tables to determine the minimum size of the grounding electrode conductor based on the size of the service entrance conductor. It is crucial to consult these tables and apply them correctly to ensure code compliance. Furthermore, the grounding electrode conductor must be connected to a suitable grounding electrode. such as a metal water pipe that is in direct contact with the earth for at least 10 feet, or a ground rod or ground ring. The connection between the grounding electrode conductor and the grounding electrode must be made in a manner that ensures a permanent and reliable electrical connection. The NEC also addresses the use of supplementary grounding electrodes, which can be used to improve the overall effectiveness of the grounding system. These supplementary electrodes can be connected to the main grounding electrode conductor or to a separate grounding bus. When using supplementary grounding electrodes, it is important to ensure that they are properly installed and bonded to the main grounding system. In addition to grounding electrode conductors, bonding jumpers play a critical role in the grounding system. Bonding jumpers are used to connect various metallic parts of the electrical system together, such as metal enclosures, raceways, and equipment frames. This bonding creates a low impedance path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The size of the bonding jumpers must be in accordance with the NEC requirements, which are based on the size of the overcurrent protection device protecting the circuit. It is important to ensure that all bonding jumpers are properly installed and tightened to ensure a reliable electrical connection. The NEC also addresses the use of equipment grounding conductors, which are used to ground non-current carrying metal parts of electrical equipment. Equipment grounding conductors are typically run along with the circuit conductors and connected to the grounding terminal in the electrical panel. This provides a path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The size of the equipment grounding conductor must be in accordance with the NEC requirements, which are based on the size of the overcurrent protection device protecting the circuit. It is important to ensure that all equipment grounding conductors are properly installed and connected to the grounding terminals. Grounding and bonding are essential for electrical safety. By understanding the requirements of the NEC and following proper installation practices, it is possible to create a safe and reliable electrical system. Always consult with a qualified electrician or electrical engineer to ensure that the grounding and bonding system meets all applicable code requirements. Remember to always de-energize electrical circuits before working on them and to use appropriate personal protective equipment such as gloves and safety glasses. Electrical work can be dangerous, so it is important to take all necessary precautions to protect yourself from electrical shock hazards. The grounding system is a critical component of any electrical installation, and it is essential to ensure that it is properly designed and installed. A well-designed grounding system will provide a low impedance path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The grounding system also helps to stabilize the voltage of the electrical system, which can improve the performance of electrical equipment and reduce the risk of damage from voltage surges. When designing a grounding system, it is important to consider the specific characteristics of the electrical system, such as the size of the service entrance conductors, the type of grounding electrode, and the presence of any sensitive electronic equipment. It is also important to consult with a qualified electrical engineer to ensure that the grounding system meets all applicable code requirements. In addition to the NEC, there may be other local codes or regulations that apply to grounding systems. It is important to be aware of these requirements and to comply with them. The grounding system should be inspected regularly to ensure that it is in good condition and that all connections are tight. Any damaged or corroded components should be replaced immediately. It is also important to test the grounding system periodically to verify that it is functioning properly. This testing can be performed by a qualified electrician or electrical engineer. Proper grounding and bonding are essential for protecting people and property from electrical hazards. By following the guidelines in the NEC and consulting with qualified professionals, it is possible to create a safe and reliable electrical system. In the context of the 10 condos served on each end with a 5-gang meter center, the proper grounding and bonding become even more critical due to the increased complexity of the electrical distribution system. Each condo unit represents a separate load in the system, and the potential for ground faults exists in each unit. Therefore, a robust and well-designed grounding system is essential to ensure the safety of the occupants and the protection of the electrical equipment. As mentioned earlier, there are two main options for grounding the condos. First, a single grounding electrode conductor to one water line, and second, separate grounding electrode conductors to each water line. While both options are permitted by the NEC, the single grounding electrode conductor approach is generally preferred for its simplicity, reliability, and code compliance. This approach involves running a single, appropriately sized grounding electrode conductor from each service entrance to a common grounding electrode, such as a metal water pipe that is in direct contact with the earth for at least 10 feet. The size of the grounding electrode conductor is determined by the size of the service entrance conductors, in accordance with NEC 250.66. In addition to the grounding electrode conductor, it is also necessary to bond all of the water lines in each unit subpanel back to the main grounding electrode. This bonding creates a low impedance path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The size of the bonding jumpers used for this purpose must also be in accordance with the NEC requirements. The alternative approach of running individual grounding electrode conductors to each water line in each unit is also permitted, but it can be more complex and potentially less reliable. This approach requires that each grounding electrode conductor be sized according to the corresponding service entrance conductor, and that all connections be properly made and maintained. Furthermore, this approach may not provide as effective a grounding path as the single grounding electrode conductor approach, as the impedance of the individual grounding electrode conductors may be higher. When deciding between the two grounding options, it is important to consider the specific characteristics of the electrical system, the cost of materials and labor, and the potential for future maintenance. In many cases, the single grounding electrode conductor approach will be the most cost-effective and reliable solution. However, it is always best to consult with the qualified electrician or electrical engineer to determine the best approach for a particular installation. In addition to the grounding electrode conductor and bonding jumpers, it is also important to ensure that all other metallic parts of the electrical system are properly bonded together. This includes metal enclosures, raceways, and equipment frames. Bonding these metallic parts together creates a low impedance path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The NEC provides specific requirements for bonding these metallic parts, and it is important to comply with these requirements to ensure electrical safety. Furthermore, it is important to ensure that all electrical equipment is properly grounded. This includes appliances, lighting fixtures, and other electrical devices. Grounding these devices provides a path for fault currents to flow back to the source, which helps to trip over current protection devices and prevent electrical shock hazards. The NEC provides specific requirements for grounding electrical equipment, and it is important to comply with these requirements to ensure electrical safety. In summary, proper grounding and bonding are essential for electrical safety in multi-unit dwellings such as the 10 condos served on each end with a 5-gang meter center. By following the guidelines in the NEC and consulting with qualified professionals, it is possible to create a safe and reliable electrical system that protects people and property from electrical hazards. Always remember to prioritize safety when working with electricity and to take all necessary precautions to prevent electrical shock hazards. Electrical work can be dangerous, so it is important to be properly trained and qualified before attempting any electrical work. If you are not comfortable working with electricity, it is best to hire a qualified electrician to perform the work. The integrity of the grounding system relies heavily on the quality of connections. All connections must be mechanically sound and electrically conductive. Using appropriate connectors and ensuring they are properly tightened is paramount. Furthermore, protecting connections from corrosion is crucial, especially in environments where moisture or chemicals are present. Using corrosion-resistant materials and applying protective coatings can extend the life of the grounding system. Regular inspection should include checking for loose connections, corrosion, and physical damage to grounding conductors and electrodes. Addressing any issues promptly will prevent the deterioration of the grounding system's effectiveness. In addition to visual inspections, periodic testing of the grounding system's impedance is recommended. This test measures the resistance of the grounding path and verifies that it is low enough to effectively facilitate fault current flow. High impedance can indicate a problem with the grounding system, such as a loose connection or corrosion. Corrective action should be taken immediately to address any identified issues. The grounding system should be designed and installed in accordance with the latest edition of the NEC and any applicable local codes. Staying up to date with code changes is essential to ensure compliance and maintain a safe electrical system. Consulting with a qualified electrical engineer or inspector can help to ensure that the grounding system meets all applicable requirements. The grounding system is not a static entity. It may need to be modified or upgraded over time to accommodate changes in the electrical system or to address new safety concerns. For example, if the electrical load in the system is increased, the size of the grounding conductors may need to be increased to ensure that they can adequately handle fault currents. Similarly, if sensitive electronic equipment is installed, it may be necessary to improve the grounding system to protect the equipment from voltage surges and noise. The role of the water pipe as a grounding electrode is significant. The NEC specifies that a metal water pipe that is in direct contact with the earth for at least 10 feet can be used as a grounding electrode. However, it is important to note that the water pipe must be metallic and must be in direct contact with the earth. Plastic water pipes cannot be used as grounding electrodes. Furthermore, it is important to ensure that the water pipe is not insulated from the earth by paint or other non-conductive materials. The connection between the grounding electrode conductor and the water pipe must be made in a manner that ensures a permanent and reliable electrical connection. The NEC provides specific requirements for making this connection, and it is important to comply with these requirements to ensure electrical safety. In addition to the water pipe, other types of grounding electrodes can be used, such as ground rods and ground plates. Ground rods are typically made of copper or copper-clad steel and are driven into the earth. Ground plates are typically made of copper and are buried in the earth. The NEC provides specific requirements for the installation of ground rods and ground plates, and it is important to comply with these requirements to ensure electrical safety. When selecting a grounding electrode, it is important to consider the soil conditions and the climate. In areas with dry or sandy soil, it may be necessary to use multiple ground rods or a ground plate to achieve an adequate ground resistance. In areas with corrosive soil, it may be necessary to use corrosion-resistant grounding electrodes. The grounding system is a complex and critical component of any electrical installation. By understanding the requirements of the NEC and following proper installation practices, it is possible to create a safe and reliable electrical system that protects people and property from electrical hazards. Always consult with a qualified electrician or electrical engineer to ensure that the grounding system meets all applicable code requirements and is properly installed.